and I gave you some examples, but that's not. So another simple divide and conquer is this exponentiation by repeated squaring, right? Which is something that we have looked at in multiple places, not only for computing integer exponents, but also in when we are computing matrix closures, right? So again, to compute a closure, you can also try repeated squaring, which will allow you to compute a particular power in log n time, right? Again, the goal is, as I go through this, for you to ask me questions if there's something here that you don't quite understand, okay? So I will assume that everybody knows merge sort, so we won't have to say anything about merge sort. Historically, right, so one of the benefits of merge sort is that you don't have to keep the whole structure in memory, whole list in memory. Okay, so you can, because merge sort only requires access to the beginning of the list at each point, right? So it doesn't really need random access, and it doesn't really need the whole thing to be kept in memory at a time. So this was one advantage. So then we looked at the master theorem. Okay, so master theorem has these three cases, and obviously whenever a recurrence, a lot of divide and conquer algorithms have recurrences that have this form, so you should be able to apply the master theorem without having to think, right? And if you try to derive something that you can compute, that you can solve using master theorem, if you try to do it from first principles, chances are that you'll run out of time for doing some other problem, right? So you should make sure that this is something that you can do without any difficulties, okay? So, and then of course there are going to be some divide and conquer algorithms for which the master theorem, it doesn't fit the form of the master theorem, therefore you need to guess and check, right? So that's the other technique that we learned. So then we looked at quicksort, and quicksort has this nature that you partition, but when you partition, you make sure that the two partitions are already in order. That is, if you finish sorting the two partitions, then you no longer have to do any kind of a merge operation. Okay. So the way this partition works is that it starts from both ends, and the pointer traverses towards the middle. The two pointers traverses towards the middle, and whenever whenever the left pointer goes over something that is above the pivot, or whenever the right pointer goes over anything that is below the pivot, that means these two elements are out of place, so you interchange them, right? So this kind of repeated interchange, right? So you move like this, and then whenever you find elements that are in the wrong part of the partition, you swap them. Okay, so you do that, and so that is your partition. And the key part of quicksort is actually the partition, because other than the partition itself, the sorting algorithm is actually very, very simple. So we talked about how to analyze the runtime of quicksort, and our point that we made was that there is a worst case which causes it to have order of n squared time, but this order of n squared time is relatively hard to get to, because skewed splits, for instance, don't really lead to quadratic time. So, for instance, even when you have 10%, 90% splits, it's fine, right? So the problem really comes when you have constant number on one side and everything else on the other partition. Right? When that happens, you have a problem. Okay. So because this is something that you cannot predict, right? So there are two things about quicksort. Is number one, if you do something simple like always taking the first element as a pivot or the last element as a pivot or some fixed element, say the middle element as a pivot, then all of those are can lead you to the worst case behavior. On the other hand, if you use a random pivot, then you're able to show that in fact it has n log n solution, or it takes only n log n time. Okay, and the way we calculate that is by saying that when you pick a pivot at random, then that pivot might fall anywhere within this the entire array, and therefore your partition would have I elements to the left and n minus I elements to the right. And if you now average over all possible places where this pivot could fall, then you end up with an equation like this, which doesn't really match your Master theorem. So we have to apply some other technique, either using essentially both of those solutions involve approximating a complex sum, complex series by a closed form solution. And one of the cases, we used a simple, approximating the log element by the upper bound, and the other case we used integral. Right? So whatever technique you use, ultimately you're able to prove that it is n log n. Okay, and part of what this leads us to is the realization that whenever you have something of the form t of n equals t of right? So whenever you have something of this form, okay, where k is a fraction and not some function of n, okay. If k is a fraction, then this sort of thing has O of n log n solution, right? So that's something that you should remember, right? So this is not Master's theorem, but it is something that you can easily prove by your guess and check, right? So you can if you substitute the solution here, and then you'll find that that solution works. Okay, so again, we'll talk about randomized algorithms later on. So maybe I won't emphasize something about randomized algorithms. And the only thing that I want you to know at this point is that quicksort you really have to use a random pivot. Okay. So then we looked at lower bounds for sorting, and there is this very interesting way to prove that as long as you're using comparisons, there is no way to sort an array without spending order of n log n time. Right? And of course, it's good to know things like this, right? Stirling approximation and so on, because it allows you to deal with some summations and series and products and so on, right? So have some idea, right? So for instance, I would like you to know that n factorial is approximately n to the power n, right? At least you should remember that. If you don't remember square root 2 pi n and divided by e and so on, that's acceptable. But at least keep in mind that this is at the power somewhere in the range of n to the power n. Okay, so then after saying that you can't do sorting in order of n log n, what we did was we said, okay, what if you have operations other than comparison, right? So by using operations other than comparison, such as division, right, you are able to do sorting in linear time. Okay, and what in the homeworks I wanted you to think more carefully about whether this is linear time or not, and so what I wanted you to realize is that if you, in most instances of sorting, the number of numbers that you want to sort is of the same order as the range of the numbers that you sort, right? And once the range and the number of distinct numbers that you have to sort are comparable, then bucket sort will still have to do, go through, log n digits. Actually, not bucket sort, but radix sort has to go through log n digits, and therefore, even though each iteration of the radix sort is going to take order of n time, because you have to go through log n digits, you end up taking n log n time. So there is, again, I guess, no free lunch, right? So at the end, you end up spending n log n time. So where bucket sort and radix sort really works is when the values get repeated. Okay, so then it works well. So another point that I want every one of you to know is this notion of stability in sorting, right? A stable sorting algorithm is one that does what?
Does not change the order if the numbers, if they are already sorted.
If
they are already like
if they are two equal keys, their order is not changed, right? So so that way you can, if you have multiple keys that you want to sort on, and then you can sort on one of the keys, and then you can sort on the second key, and you will have the results sorted on both keys, and that's and we had this example of sorting cards. Okay, so and then again another place where this kind of radix sort works very well is when you have to sort strings, because once again the number of distinct values for each character is limited, and therefore it's a place where you can very easily apply these algorithms, and you can get a nice nice bound of linear in the size of the input, right? So that's the nice thing about this algorithm, that given a set of strings, well, obviously the size of the input in that case is the sum of sizes of the strings that are given to you, right? And so now you want a solution that is linear in that. Obviously you can't do better than that, because just to read your input is going to take linear time. So the next problem we looked at is selecting the kth largest element. So the idea is that in order to select the kth largest element, the naive approach is to sort it and then pick the kth largest. That takes n log n time, but you can do better, and in fact you can do linear time selection of the kth largest elements. And the simplest approach is to use the quicksort algorithm, except that you don't sort both sides. You only call yourself recursively on one side, on the sides in which the kth element is residing. So if k is less than the partition, the place where things get partitioned, then you will call the quick select on the left half. If it's greater, then you'll call quick select on the right half. So you have a recurrence of the form well, hopefully, right? T of kn, where it's a fixed fraction of n, and then this has again a linear solution. And once again, just like this case, right? So we can show that. Let's say if you remove that, then this is O of n solution, right? So if you don't have both terms, you just have one side, right? One of these two terms, then this recurrence will become O of n. If you have both elements, then it becomes O of n log n, right? So that's something that, again, you should some of these things I want you to again remember. That was the reason why I gave it to you in the quiz. It's not something that I want you to sit around and analyze for half an hour and then figure out that this is the case, right? Because then it might take you too long. There are a few things that you can sort of have a good enough understanding and a good enough recollection that you don't have to recompute it during the exam. So on the other, but the quick select itself only provides linear time selection in a randomized setting, right? So but there is no worst case linear time bound. So we then talked about this other technique, which gives you linear time worst case, and the way you do that is by using this median of median techniques, where you apply quick select in two passes, right? First you do quick select to compute the median of medians, and then you choose the median of medians to partition and rerun the quick select algorithm. Okay? So now, because you chose the median of median as the partitioning element, you are guaranteed that the whole thing will take linear time. So then we talked about heaps. Things that you need to remember about heaps is that conceptually it is a tree-like data structure, but it has an efficient representation in terms of arrays, right? And this is why it's very popular, because you don't have to do pointer chasing in order to use heaps, right? So as I mentioned to you before, pointer chasing is quite expensive on modern architectures. So tree data structures are not, they don't work. They don't necessarily work well with caches and so on. So to have an array data structure without explicit pointers is very advantageous, because we don't have to do that pointer chasing. Okay? So we understand heaps in terms of a few operations, such as heapify, right? So build a heap given a unsorted array, insert a new element, or delete the maximum or minimum. Again, heaps can be organized so that the first element is maximum, or they can also be organized so that the first element is minimum. So in this case, we call it a max heap because the top element is the max. Okay? And in the max heap, you are interested in delete max, and also you are interested in knowing what is the maximum element, and you're interested in inserting. So those are the operations that the heap allows. And in terms of a data structure, an interface that gives us essentially a priority queue, right? Because we are able to insert, and then we can ask for the lowest priority or highest priority at any time. Okay, and then we can insert at any time. So the key property is that to build a heap initially you take linear time, and then to insert you take log n time, to delete max you take log n time, and if you just want maximum, then it's constant time. Right? So we didn't look at this example, so you don't have to worry about this. Then we looked at matrix multiplication. Yeah.
About T of n equal order of n plus T of kn. This is order of n, but depends on the value of k, right? So
if k is a fraction like 0.1, 0.05, all of that is fine.
But it can be like if it is 0.9, it won't be.
0.9 is fine, right? It just
yeah,
shouldn't be.
But
so what is not allowed is that k is a function of n. So if you say, well, k is 1 by n, well, obviously that's not going to work, right? But if k is a constant, then it's going to work. Okay. So we looked at matrix multiplication, where there is this idea that you do a divide and conquer, you take a matrix, subdivide it into 4 submatrices, and then you do the multiplication. But if you do it naively, then you end up making 8 multiplications on n by 2 by n by 2 arrays. So unfortunately, you end up with the order of n cubed time. But the key point is that there is a way of doing this without making 8 multiplications, but instead 7. And once you're able to do 7, then you are able to get this recurrence, right? T of n equals 7 times T of n by 2 plus O of n squared, which if you plug into your master theorem will tell you is that this has this complexity log 2 to 7, which is significantly, well, maybe not significantly, but it is definitely better than order of n. I mean order of n cubed. So then we said we could apply the same technique to integer multiplication, where we could divide the integer into each integer into 2 smaller halves, and then again the naive multiplication would have 4 multiplications on n by 2 bits, which unfortunately will again have the same n squared complexity. But then there is this trick where you can get away with just 3 multiplications, and now again you have an instance of the same type of recurrence, right? And so you apply master theorem and it gives you this solution. And this n to the power 1.59 obviously looks much better than n squared. Okay. So then what we did was we talked about how integer multiplication and polynomial multiplication are very similar to each other. And in fact, when we do our long multiplication by hand, what we are doing really is essentially evaluating, doing a polynomial multiplication would be identical to how we do long multiplication by hand. So using this similarity, then what we said was that we can think about integer multiplication more generally in terms of polynomial multiplication. And when you do that, then you have some tricks that you can pull out, because with polynomial multiplication, you have certain properties of polynomials that allows you to evaluate the polynomial at n points, right? And now you're given a polynomial p1 and a polynomial p2. Each of these polynomials can be evaluated at n points, and then you can do a point-wise product of these polynomials, and then you get the points on the product polynomial, and then you invert that in some way, and you'll be able to get the resulting polynomial, and all of this could be faster, and then the rest of the time we spent on showing how one could really make this faster. Okay, so there is a series of 2 algorithms which use this idea to reduce the number of multiplication, with Karatsuba being 2, which, but the idea is basically the same. So somehow you evaluate it at some number of points, and then from that you are able to, that allows you to do the multiplication with, somehow get away with fewer recursive calls, and as a result, the overall algorithm ends up having a lower complexity. Okay. So we also briefly discussed FFT as a generalization of this technique, but I'm sure you may not remember a lot, and I don't think we did any homework problems related to that. Did we? Or we don't remember? No, we didn't do, right? I'm pretty sure we didn't, or at least there was no problem that was required to be submitted. I don't know whether there were some problems that that you didn't need to submit. Okay, so that's See, we're done preparing, one unit is done, right? So we have only 2 more units to go, and then you're ready for the exam. At the rate at which we are going, you should be able to start at 3:30. Okay, so let's so any questions so far? So we went over basic, this is basically meant to be a review of graphs. So because the whole thing is a review, I'm not going to talk about this too much. So we have multiple ways of representing graphs, adjacency matrices and adjacency lists and so on. And then we talked about depth first search. Okay, so I mean, presumably everybody came into the course knowing what depth first search was. We did talk about a few things on top, such as the pre-numbers and post-numbers and some properties of depth first search in terms of these pre and post-numbers. Right? So that's something that you should be able to know. We had a few problems where by using pre and post numbers you can answer certain questions quickly, such as is this node a descendant of this other node, right? So I think there's a problem where you're given a tree and you're asked, okay, can you pre-process the tree in such a way that somehow given 2 elements you can tell immediately whether one element is a descendant of another. And of course, if you think in terms of depth first search and so on, then it's pretty obvious. But if someone just gives you that problem with no such background, then it might seem like magic, right? So how do you do in constant time? How do you know whether something is a descendant? You need to do that in constant time, and pre-processing time is not also unlimited, right? I mean, if you're given unlimited pre-processing time, you could just say, oh, for each node I'll just create an array that consists of all its children or all its descendants. Then of course you can very easily look that up quickly, right? On the other hand, if you are told that you can only keep a limited amount of information at each node, only a constant amount of information at each node, and then it's not entirely obvious, but once you see the solution, then you realize, wait, this is a good way to keep information about the structure of a tree, so that in applications where you quickly need to make a decision whether something is the descendant of another, then you have a way of doing that. Okay, so we also talked about DFS on directed versus undirected graphs, and in undirected graphs you have 3 types of edges in the DFS tree, and but the cross edges always go from right to left, right? So this is something that we discussed, and I would expect you to remember. So we discussed biconnectivity, okay, briefly. So I want you to know what is biconnectivity, right? And we also discussed an algorithm for computing these so-called articulation points that join together any 2 biconnected components. Okay, so the reason why I covered articulation points is that this algorithm actually is simpler than the algorithm for finding strongly connected components, which is similar but a bit more complex. Okay, but you need to remember, more important than the algorithms themselves, you should know that biconnected components can be identified in linear time using DFS, and again, strongly connected components in a directed graph can also be computed in linear time using DFS. Right? So that's more important than knowing exactly how to find them. Right? So you should know the definition, of course, of what biconnected component means and strongly connected component means. You also should be able to and you should also remember what is the complexity of this algorithm. If you don't remember exactly what is the algorithm for computing them, that's okay. Okay? But remember that even though you don't know the algorithm, if I give you a graph, you should be able to say, what are the biconnected components, right? Because that you can do by knowing the definition of what it means to be biconnected or strongly connected, right? So from that definition, you can manually solve the problem. But if you can be sure I won't ask you a question that says, write an algorithm for computing strongly connected components, right? For the matter, I'm unlikely to ask you any question which asks you to repeat an algorithm that we studied in class in its, in its exact form, right? Somehow there needs to be some variation. More likely, you will encounter problems where by applying one of these algorithms, you will be able to solve it, right? And many times, you don't have to, write the pseudocode for something unless the nature of the problem, is such that it requires you to spell out in detail exactly how you're going to solve the problem. Many times the problems are going to be of the nature, okay, if I use this technique here and that algorithm there, then I'll be able to get a certain complexity. Okay, and again, in algorithm courses, right, the way you solve, many times you are given, okay, design an algorithm which has a certain complexity, and you need to be familiar with the complexities enough that that given complexity itself directs you to the possible algorithms, right? Because if you have to know that, okay, if I need this, then that limits my choice of which component algorithms that I'm going to use. And once you know that, then it makes it that much easier to solve the problem, right? So you need to. This is why complexity of different algorithms is something that you should really it should be really integrated into your mind. Okay, so that's so we talked about breadth first search, and whereas a depth first search is recursive, which means that it uses a stacked data structure. A breadth first search uses a linear a linked list as a data structure. So if DFS is LIFO, right, last in first out, and the BFS is FIFO, right, first in first out. Okay, so those are the things that you should remember. And the other point about BFS is that if you want shortest path, where shortest is defined in terms of the number of edges, not the edge weights, right? So if you want the shortest path in terms of how many edges are between two vertices, then BFS will compute shortest paths. Okay. The other thing which I really like, and I think is very useful in understanding graph algorithms and remembering them, is this association between Boolean matrices or other types of matrices and the graph representation, and how operations on this matrix, right, this adjacency matrix, can in fact lead you to conclusions about connectivity or the presence of paths in a graph. Okay, so so for instance, we said that if if you define a closure of a matrix as this sum a to the power 0 plus a to the power 1 plus a to the power 2 and so on, right? Then we said an element in this closure will be 1 if and only if Vj is reachable from Vi, right? So Dij will be 1 if Vj is reachable from Vi. Okay. One thing that you should remember though is that the things that this matrix operation counts aren't necessarily what we would call as well-defined paths, right? Because the matrix doesn't care if you go back and forth between two vertices like 20 times and then you go here, right? That is still somehow in the calculation, everything is somehow allowed, right? So you take some Boolean OR operation, well, that says I can either go want, if you look at, let's say, a to the power 5, okay, which means that you have to follow 5 edges, right? These 5 edges are not distinct, right? Because the matrix formulation doesn't really keep track of any of that. So you could really, do this a few times and finally get out of that. I guess this is the wrong solution. It should be here, right? So U, V, W, according to the matrix, there is a path of length 5 from U to W, which involves going back and forth between U and V 4 times and coming to W, right? So but this is not a path that we would be particularly interested in, and this is why you cannot use a matrix formulation to solve certain problems. Like, for instance, if I say, tell me whether there is a path of length 5 between U and W, well, you can't just compute a to the power 5 and check that. Okay, so you need to be careful in how, while it can tell you about connectivity, it can also tell you about shortest paths, which by changing the interpretation of pointwise multiplication and pointwise addition, we can also use this matrix operation to compute shortest paths. But there is a limit, so you always have to keep in mind that there is this problem. It doesn't really allow you to say, if I use the edge once, I cannot use it again, right? So you cannot capture that in this matrix formulation, and therefore certain things where you assume that the path doesn't go over the same edge again and again, well, that cannot be done using this relationship between matrices and graphs. Okay. So by the way, we said, so this is for shortest path, we simply have to redefine what we mean by plus and star, right? So normally when we work with matrices, by plus we mean integer or real number addition, right? So integer or floating point addition, and multiplication is again integer or floating point multiplication. Okay, whereas you could define it to be a different set of operations where adding 2 elements of the matrix is interpreted as the minimum, taking the minimum of those 2 elements, and multiplying 2 elements of the matrix is interpreted as an addition. Right? So once again, you may remember very briefly that we talked about graphs and not graphs, groups and rings and so on. And while you may not remember, and I don't necessarily expect you to recall all of that in your exam, what I want to convey to you is that those abstractions are actually very useful, and you'll find them appearing in multiple places. And one place where it appeared was when we were doing the FFT, and in order to do multiplication in FFT, FFT itself is originally developed, Fourier transform itself is originally developed as something that operates on complex roots of unity, which you can represent only using floating point numbers. But essentially, by taking the essential properties of complex numbers and finding an integer domain where those properties still hold, you are able to now avoid the problems with working with floating point numbers, which is that you have to deal with inexact computation, right? So when you have floating point numbers, whenever you do an addition or multiplication, you lose precision, right? So on the other hand, if you work with integers, well, you don't have any loss of precision, right? So by making use of these abstractions like groups and rings and fields and so on, one can take a problem which you understand in a particular domain, such as integers or floating point numbers or complex numbers, and recast it on a different domain where you could potentially avoid some of the drawbacks. And this is again another such case where instead of applying your matrix operations on integers, you are applying it on in a different domain. Okay, so so that's all that we have to say about the overview of graphs. So any questions? See, they're all very clear, or you're totally lost. Which one is it? Okay, so it should be the case that it's all very familiar. So we will keep moving. So then we covered greedy algorithms, right? So greedy algorithms are used to solve optimization problems. And again, greedy means you're trying to make a locally optimal choice without doing the difficult work of identifying what is globally optimal. And so most of the time it doesn't work. So you need to be careful in using greedy strategies. And especially if you want a good algorithm, then you really need to actually take the effort of proving that locally optimal solutions or locally optimal choices actually do result in globally optimal solutions. Okay? But of course, the reason why we like greedy is because the algorithms can be fast because you're doing a local search instead of a global search, right? And the contrast is in dynamic programming where it's like a global search. So the algorithms that use dynamic programming tend to be generally more expensive, and so but then they work on a larger set of problems and are able to provide optimality because in fact we start off by writing an equation that captures what it means for a solution to be optimal, and then we just simply use that equation to compute the optimal solution. And therefore in dynamic programming, ensuring optimality is quite easy. It's just that it's a little bit more, it's often much more expensive. Whereas in the case of greedy, the algorithm itself is simple and has lower complexity, but you need to sit down and prove that in fact it's efficient. I mean, that it is optimal. Okay, so we start out with some examples like making change, and I asked you to think about the conditions under which this is optimal. Did anybody come up with a condition?
Is it when the numbers are factors?
Well, if you come up with a good answer, let me know, because I'm not, so I think it is relatively easy to identify cases where it is optimal, and you can also give sufficient condition when it's going to be optimal. So for instance, if if they are powers of 2, right? Well, it's trivially optimal, right? Or if is that what you said? Multiple of other?
I feel like there's something to do with factors, but
factors, not multiples of each other. If each coin needs to be a multiple of the lower numbered coin, then this algorithm would work.
Then it would definitely work.
Right? But that's too strong a condition and it's uninteresting, right? So yeah, so what? Right? I mean, especially for instance, if you say, they have to be factors of 2, then that's like writing a binary number and then, looking at each digit one by one and then say, oh, okay, so I need to give, 1 of this and okay, these 3 digits are 0, so I don't give you any of that, and the next one and so on. So it's it's really not satisfying if you said one is a multiple of the other. Now, under what other conditions this is optimal, I don't quite know. At least I don't remember at this point, and I don't recall that there was an easy way to characterize that. Okay, but it is still a good exercise to think about. So again, both in greedy algorithms and dynamic programming, you need this optimal substructure which relates the optimal solution for the problem